Welcome, dear students and all learners on this e-learning platform. Myself, Dr. Abhinav Srivastava. In this presentation, I am going to briefly discuss periodic position, electronic configuration, and oxidation state of d block elements or transition elements, along with some relevant multiple choice questions. So, as per IUPAC, the transition element or ions may be broadly defined as elements or ions having partly filled D or F subshell. If D subshell is partly filled, then the elements will be known as D block element or transition metal elements. Here the penultimate D subshell are successively filled. If F subshell is partly filled, the elements or ions are known as F block or inner transition elements. It may constitute lanthanide and actinide series. In modern periodic table, transition metals or D block elements are placed in between S block and P block elements. Elements of S block are highly electropositive metals which prefer to form ionic bonds, while elements of P block are prefer to form covalent interactions. So, position and properties of D block elements lies in between S and P block elements. D block elements are good metals like S block elements and prefer to form covalent coordinate interactions in their coordination complexes like P block elements. In this context, in 1921, English chemist Charles Bury coined the term transition to D block elements as he observed certain transformations in their properties by successive addition of electrons in their penultimate D subshell. So, in modern periodic table, transition metals or D block elements are placed from group 3 to group 12. When we talk about period, D block elements lies in 4th period, 5th period, 6th period and 7th period. There are these periods are also known as respective transition series, while inner transition elements or F block elements are placed separately in periodic table. In D block elements, as we discussed earlier, they are placed in 4th period, 5th period, 6th period and 7th period. These elements make up 3 complete rows, that is 3D, 4D, 5D of 10 elements each, which are naturally existing and also known as heavy metals. While the 4th row, which is placed in 7th period, is of transactinides, which are generally synthetic D block elements and also known as super heavy metals. So, the first transition series, that is 3D series of D block elements, lies in 4th period, which starts from scandium 21 up to zinc 30. Second transition series or 4D series lies in 5th period. It starts from yttrium atomic number 39 and goes up to cadmium 48. The third transition or 5D series is placed in 6th periodic table. The first element of third transition series is lanthanum, which is basically a prototype element of lanthanide series. After that, from hafnium 72 up to mercury 80, this third transition series extends. While in fourth transition series, The first element is actinium 89, which is prototype element of actinide series, that is inner transition element series. After that, from Rutherfordium atomic number 104 to Copernicium atomic number 112, this fourth transition series goes on. So overall condition is what? The d block element or transition elements are placed from group 3 to 12 and in respective 4th period, 5th period, 6th period and 7th period in periodic table. Now let us discuss regarding electronic configuration of transition elements. There are certain rules and conditions which play a key role in prediction of their electronic configuration. If we look into general electronic configuration, then the penultimate d subshell, that is n-1 d subshell, contains 1 to 10 electrons, while the outermost s subshell, that is ns subshell, may contain 0, 1 or 2 electrons. Here n is principal quantum number. For a free atom, the ns orbital is normally filled prior to the penultimate d orbital as per Aufbau rule. All the 5 degenerate penultimate d orbitals first singly filled up to d5 configuration. After that, pairing of electron get occurs from d6 onwards as per Hund's rule. Additionally, achievement of extra stable electronic configuration, that is d0, d5 or d10 configuration, shielding effect, inter-electronic repulsion, nuclear electronic attractions or exchange energy forces are some other influencing factors which causes irregularities in routine electronic configuration at some places in different transition series, which we will discuss later. Let us start with the electronic configuration of 3D series, that is first transition series. In this series, there are 10 metals: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. In this series, the penultimate 3D subshell is successively filled from 3D1 configuration to 3D10 configuration, that is from scandium to zinc. In between, chromium and copper are found to show irregular trends while filling the electronic configuration. Chromium is supposed to have 3d4 4s2 electronic configuration, but to attain extra stable electronic configuration, that is 3d5 4s1, one of the electron from 4s subshell moves into the penultimate 3d subshell. This phenomena occurs to attain the extra stable 3d5, that is half filled electronic configuration. Likewise in copper, whose electronic configuration is supposed to be 3d9 4s2, but the actual electronic configuration is 3d10 4s1, because to attain extra stable electronic configuration, that is d10 electronic configuration, one electron from 4s subshell moves into penultimate 3d subshell. Therefore, chromium and copper in first transition series show abnormality in their electronic configuration. When we move into 4D series, that means second transition series, here yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium elements are placed, having atomic number 39 to 48 respectively. In this series, the electrons are successively added in penultimate 4D subshell. Here, molybdenum, like chromium, shows irregularity in normal trend of electronic configuration. That is, it, it has 4d5 5s1 electronic configuration. This occurs to attain the extra stable electronic configuration. In this series, the lower elements beyond atomic number 44, they have certain irregularities in their electronic configuration, especially palladium having atomic number 46. It shows abnormal electronic configuration 4d10 5s0. It It is expected to show the routine electronic configuration 4d8 5s2, but it shows 4d10 5s0 electronic configuration. The reason may be attributed that with increase in atomic number, there occurs very little difference between excitation energies of 5d, respective 4d, 5s, or 5d, 6s. Therefore, electronic transitions occur more readily. That's why, to attain extra stable electronic configuration, these elements rearrange their electronic configuration. In 5D series, that is third transition series, the elements are lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, and mercury. In this series, the electrons are successively added in penultimate 5D subshell. This series shows some interesting trends. Unlike chromium and molybdenum, tungsten has regular electronic configuration. It shows regular filling of electrons in its 5d subshell and 6s subshell. Its electronic configuration is 4f14, 5d4, 6s2. While the lower elements, platinum and gold, uh, follow to attain their extra stable electronic configuration, that is D10 electronic configuration. So here a genuine question arises: why tungsten, unlike chromium and molybdenum, possess idealized electronic configuration? The reason may be in group 6 of transition elements, chromium, molybdenum, tungsten are placed. Here, relativistic quantum effects lead to the stabilization of 6s subshell and destabilization of 5d subshell, which directly favors the population of 6s energy level over 5d. Therefore, in tungsten, there occurs regular electronic configuration. On the other hand, in chromium and molybdenum, the extent of interelectronic repulsions among the sets of 3d and 4s is generally larger than the repulsions in 5d and 6s orbitals, because the 5d and 6s orbitals are thought to be more diffused. Hence, to minimize the extent of electron-electron repulsion, that is interelectronic repulsion, chromium and molybdenum prefers to adopt a configuration D5S1 in which exchange energy is maximized. Thus, the extent of interelectronic repulsion get minimized. This is the reason why chromium and molybdenum have D5S1 electronic configuration, while tungsten has D4S2 electronic configuration. Their penultimate shell. Now, we are going to discuss some general oxidation states of transition elements. Transition elements are known to exhibit variable oxidation state and variable valency. Here, the 4s orbital is more diffuse than the 3d orbital. Due to interelectronic and internuclear interactions, the 4s orbital gets higher in energy than 3d orbital after filling. This means that when electrons are lost to form cations, then it is the 4s electrons that are lost first. For example, if we write the electronic configuration, ground state electronic configuration of iron 26, that is 3d6 4s2. Now, when iron forms is di-positive cation, that is ferrous ion, then in this formation, first these 4s electrons get lost and the formation of di-positive cation of iron takes place. The electrons leave in respective successive steps. When ferric ion, that is tri-positive cation, is formed, then the electrons lost from the d subshell, that is penultimate d subshell. So, while predicting their stable oxidation state, we will have to consider that the electrons will be first lose from 4s and after then the degenerate 3d subshells in a regular way. There are some interesting trends while comparing general oxidation state of 3d, 4d and 5d. In 3d series, that is first transition series, there are variable oxidation states of respective metals. The black bubbles are showing the stable oxidation state, while the white bubbles are showing comparatively less stable oxidation state of respective metal. For example, scandium. Scandium, the most stable oxidation state of scandium is 3 plus, while in titanium it may exist in di-positive, tri-positive or tetra-positive cation. In 3d series, the maximum oxidation state, that means variation in oxidation state, is shown by manganese, which forms variable cations starting from 2 plus oxidation state up to 7 plus oxidation state. In this series, zinc is only stable in 2 plus state. In 4d series and 5d series, the similar trends of variable oxidation states and variable valencies are seen. Here I would like to consider the trends of ruthenium and osmium. Ruthenium, the element of 4d series, while the osmium, the element of 5d series, show maximum oxidation state amongst all the transition elements, that is +8. This is an important property in chemistry of ruthenium and osmium. If we wish to generalize the oxidation state trends amongst transition element, we may state that transition elements are generally show +2 and +3 oxidation states. In 3d series, manganese atomic number 25 show maximum variability in oxidation state, that means from +2 to +7, while ruthenium, that is element of 4d series, and osmium, element of 5d series, shows the highest oxidation state, that is +8, in their compounds ruthenium tetroxide and osmium tetroxide respectively. Another general trend is that there is an increase in number of oxidation states in going from left to right in a period, and it attains maxima in between the middle section of the period. For example, in 3D series, when we move from scandium to manganese, we will get the maxima at manganese. Therefore, manganese show maximum variability in its oxidation state. There is an interesting fact also that the following transition metal elements or ions are not considered as a typical d Blanc element, because as per IUPAC definition they lack partly filled d subshells. Earlier we learned the definition of d Block elements, that they must contain partly filled d subshells. But in scandium 3 plus it has d0 configuration, that is there is no electron in d subshell, while in zinc or zinc dipositive cation there occurs d10 configuration. This configuration is not partly filled, partly means incomplete. Zinc or dipositive cation of zinc shows fulfilled electronic configuration. Likewise, cadmium and mercury as an element or in their dipositive cation also show fulfilled d electronic configuration. Therefore, these species are not found perfect on the definition of d Block elements. In metal carbonyls, generally transition metal atom exists in its zero oxidation state. It is a general trend. Another important aspect of oxidation state and chemistry of transition metal elements is that higher oxidation states of elements of 4D and 5D series are more stable than the corresponding 3D row, and these elements of 4D and 5D prefers to form stable oxyanions like molybdates, pertectinate, tungstates, perrheniates, etc. While the oxyanions of 3D row, that is chromate or permanganate, are good oxidizing agents. If we talk about relative stability of various oxidation states in transition series, then we found the fact that to attain extra stable electronic configuration, that is D0, D5 or D10, elements may acquire easy transformations, or their respective D0, D5 or D10 electronic configuration become extra stable in comparison to their other oxidation states. For example, titanium tetrapositive cation having D0 configuration is more stable than its tripositive cation which has D1 configuration. Likewise, manganese dipositive cation having D5 configuration is more stable than manganese tripositive cation. In the same way, ferric cation having D5 configuration is supposed to be more stable than its ferrous species which has 3d6 electronic configuration. In the same way, copper monocation, that means cuprous ions, is comparatively more stable than its dipositive cation having D9 configuration. So these are some interesting trends found in the study of oxidation states of transition metal elements. Now we will try to perform some multiple choice questions based on these facts and findings. So if we wish to perform our knowledge on a certain scale, then we will have to check some questions and answer them. In this concern, question number 1 is: in transition elements, the incoming electron occupies penultimate d subshell in preference to option A n s subshell, B n p subshell, n minus 1 p subshell, or n plus 1 s subshell. This knowledge we gained in our earlier slide, where the penultimate d subshell is going to filled prior to what? Prior first the s subshell will filled and then this penultimate. So the answer will be NP, because after filling of NS subshell, the filling of NP subshell is going to be expected. But the in that place, the penultimate D subshell of the same quantum number is going to filled. So the answer will be NP. Another interested question is that the elements of 3D, 4D and 5D series in periodic tables are called as. Options are normal elements, representative elements, transition elements, or inner transition elements. Answer is very easy. The elements of 3D, 4D and 5D series are comes under the class of transition elements. Question number 3. Which one of the following 3D elements show maximum oxidation state? Obviously, the answer will be manganese. Why? Because it shows variable oxidation states from +2 to +7. Next question is question number 4. Which of the following stable cation is not considered as a typical transition metal ion? Options are dipositive cations of zinc, manganese, iron or copper. So answer will be zinc 2 plus. Why? Because it contains fulfilled D10 configuration, and as per definition of pure transition elements, it should contain partly filled D subshell. So answer of this question will be zinc 2 plus. Question number 5. Maximum oxidation state of osmium is. Options are +7, +3, +8 or +6. So the right answer will be +8. As we discussed earlier, osmium, the element of 5D series, show maximum oxidation state +8 in its osmium tetraoxide complex. Next question is question number 6. Which of the following has a unique electronic configuration? Chromium, zinc, lanthanum or palladium? Answer will be palladium. Why? Because unlike nickel, it contains D10 as 0 configuration. It is supposed to have D8 as 2 configuration, but it attains D10 as 0 configuration to attain extra stability. That's why right option will be palladium. Next question number 7. Anomalous electronic configuration in 3D series are of. Options are chromium and iron, or chromium or copper, or scandium or titanium, or copper or zinc. The right answer will be option B, chromium and copper. As we discussed earlier, chromium and copper show anomalous electronic configuration, that is D5s1 and D10s1, to attain extra stable electronic configuration. Next question is question number 8, in which we have to arrange in correct order of stability of dipositive cations of manganese, iron and chromium. This is very tricky question because these three dipositive cations are very stable in respective conditions. So the right option will be option A, in which manganese dipositive cation will be more stable in comparison to iron dipositive cation, and which in turn is more stable in comparison to chromium dipositive cation. The reason may be manganese 2 plus has extra stable D5 configuration, Therefore, it is most stable. While among Fe2 plus and Cr2 plus having D6 and D4 configurations, since exchange rate of Fe2 plus is greater than Cr2 plus in aqueous medium, therefore stability of Fe2 plus will be far greater than chromium 2 plus in aqueous medium. That's why the stability trend will follow. Manganese 2 plus will be more stable than Fe2 plus than Cr2 plus. Then I would like to refer some significant textbooks with respect to the presented topic. Basic Inorganic Chemistry, either by J.D. Lee or Cotton and Wilkinson or Hui and Keeter, are some important books regarding inorganic chemistry, while some books of some Indian authors like Puri Sharma and Kalia or S.C. Kheda are also helpful to gain knowledge. You may prefer any of these books which may be easily available to you. At the last, I would like to thank principal of our home institution as well as head PG Department of Chemistry, Lucknow Christian College, Lucknow, for their ever helping attitude and encouragement. Thank you for your patience hearing. Stay home, stay safe, stay connected, and keep learning. Thank you very much.